Okay, so before we do the linear functions lesson, make sure that you have completed the relations and functions, which is lesson 3.1, using the video and following along in your workbook to complete the examples and the work in there. If there's something that you don't see that matches something in the video, then you can just work it off off onto the side of your book. So this is linear functions lesson 3.2. Objective is I will be able to identify, evaluate, graph, and write linear functions. Terms you'll need to be familiar with are function notation and linear function. Here's a refresher on what a function actually is. Remember, we looked at this machine and thought about what would we expect to happen if we had pressed B2. We would expect to get Cheetos. How about D5? We would expect to get the Hershey's chocolate bar. If you pressed A4, would you expect to get an apple? No, we would expect to get Fritos because there is a function happening within the machine. We give it an input and it gives us a specific output. The machine has a function. You put something in, something happens, and something comes out. Let's determine if these are functions or not. So in our last lesson, we looked at the definition of a function being that every input has only one output. So our x values should go to one y value. When we see that we have two of the same number, such as this one, going or the same number, but 2 is going to 4, the other 2 is going to 8, that is not a function. So over here, we have a function, not a function. And then looking at these x values, each x value has only one y value. There are no repeats for x, so this is also a function. Also thinking about, is it one-to-one? Do we have multiple y values to different x values? Or the same y value to different x values? And you can see that we don't have any repeats here either. This is one-to-one. This is not a function, so it is not one-to-one either. And these y values are all different. So every input has one output. There are no repeats. It is definitely also one. So this is the first section in your book for lesson 3.2 or 3-2. It's on page 53. So turn there. And let's look at this example. The flow chart shows the steps of a math puzzle. You think of a number, multiply that number by 9, subtract your original number, and divide that number by 4. This is a math puzzle. So try the puzzle with 6 different integers and record those in your workbook. Record each number you try and the result. Make a prediction about what the final number will be for any number and explain. And lastly, would your prediction be true for all numbers? And explain. And at the end of your page there on page 53, you'll notice that you have a habits of mind prompt, and it's a question asking you, is it possible to find a counterexample? I do want you to complete that as well. A counterexample is something that is an exception to the rule. So if you can think of a time when this wouldn't always work, that would be coming up with a counterexample. So go ahead and take a minute to try this, pause the video, fill it out, and then continue when you're ready. Okay, our essential question, how can you identify a linear function? Example 1, so you're now following along, you're going to do some try it starting on page 54. So write the equation y equals 5x plus 1 using function notation. Remember that a function is a rule that takes an input or an element in the domain and maps it to an output or an element in the range. Remember, x is domain, y is range. This here. Function notation is a method for writing variables as a function of other variables. The variable y becomes a function of x, meaning the variable x is used to find the value of y. This helps distinguish between different functions, and the relationship between the variables can be used to solve problems and make predictions. Here's our function kind of machine that we've seen before. Element of the domain is our x values. Goes in, we perform the function, and our function of x becomes our f of x, function of x becomes our y value, our output. The function f is defined in function notation by f of x equals 5x plus 1. Should be over here. Basically, y becomes f of x. Evaluate g of x equals 5x plus 1 for x equals 3. So now we've got this x value, this domain of 3. So we're going to substitute the input for every instance of x in the function and see what we get. So in this case, we can just generate some values. So we could start simple with 0, 1, 2, 3, 4. We'd apply this function every time. So here's my 3. If I plug this in, this is going to relate to that. 5 times 3 is 15. 15 plus 1 is 16. So my output is 16. And you can fill in the rest of those if you've done this in your notes section on page 54. This one would be 1, 6, 11, and 21. And you can start to notice patterns here. It's increasing by 1 each time. And over here, you can see it's increasing by 5. Just to start thinking about that for future. Another way of looking at things is you have f of x equals 3x plus 4. The name of the function is the letter that's in front of x. This expression here on the right side is the function rule. And x is what tells us what number to plug into the function to evaluate and get the y value. So f of x means the output of function f when the input is x. The output of function f when you have this input. F of x is just another way of writing y. So now it's your turn. Try it on page 54. Evaluate each function for x equals 4. You do not need to make a table. You are just focusing on x equals 4 and then evaluating the equations. Pause it and then come back when you're done. Okay, you should have shown -2 times 4 equal or minus 3. This is -8 minus 3. You get -11. 7 times 4 is 15. You get 28 plus 15. Add those together and should actually put this function notation in here. G of x equals -11. H of x equals 43. Whoa. What happened? 43. Okay. Functions can be represented in various ways. So you've got the words, the output is 3 more than twice the input. If you look, that's the function for that. 3 more than twice the input. A table, you would generate some values, perform the function. So you plug in 0, you get 3, you plug in 2, you get 7, you plug in 4, you get 11, you plug in 6, you get 15. And then you would graph it. Now my graph is a little messed up, but when you graph it, you can see that it starts at 0 and 3, which means this would be my x-axis. The y-intercept is 3 because x is 0. So just relating all of those pieces together. The cost to make bracelets is shown in the table below. Can you determine the cost to make any number of bracelets? Use y equals mx plus b. This should look familiar. This is slope-intercept form. Okay, this is when you need to write a linear function rule. This is what we're focusing on next. So if we go back, we're looking for the pattern. What's happening, and this is giving us sort of a clue. We're going to do some multiplication and some addition each time. So think about what that would be. And it's not saying function notation, so you can go ahead and write y equals, but we could also put f of x. So if you look, we see that these are being increased by 1 each time. That is really sloppy. And then here, the pattern is being increased by 15. Here. The question is, how do we go from x to get y? What are we doing to x to get y? And if we look, we're going to be multiplying by 15 and adding 2. So we have 15x plus 2. And that works every time. 1 times 15 plus 2 is 17, and so on, and so on, and so on. Okay. Now it's your turn to try it. Find the patterns. Go ahead and identify what's happening between your x values or your domain and also your range of values, your y values. And you can write the linear function in y equals form, just like slope-intercept. And we will check those later. Not going to check your answers every time, but you can certainly check in with those later. Just give yourself some practice. Pause it, work it out, and then come back when you're ready. Example 3, Tamika records the outside temperature at 6 a.m. The temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? So we're going to do 4 steps here. We're analyzing a linear function, and we're going to do that in 4 ways. First, write a function that models the relationship in the scenario. Then we're going to sketch a graph of the function. Then find the value of y when x equals 8. And then answer, does the function realistically represent the temperature for the domain of x being greater than 0 but less than 24, which is the number of hours in a day? So let's take this one step at a time. First, we need to write a function that models this scenario. So what do you think that would be? And if you're thinking, I'm going to use function notation because it says write a function. Well, we know it's increasing 2 degrees every hour, so that would be 2x. And we're going to take away the temperature at 6 a.m. So it increases 2 degrees Fahrenheit each hour, and the temperature at 6 a.m. is going to be -3. So that's where we get these values. you see, there it is there. So that would be like our y-intercept. Okay, B, sketch a graph of the function. I don't know if, no. Okay, so I'm just gonna quickly make a graph and thinking about the slope-intercept form, which is what we wrote, which was y equals 2x minus 3. I know that I'm going to be starting here at -3. From there, I have a slope of +2, so I am, one second, I'm going up 2 over 1, up 2 over 1, up 2 over 1, and you can see the pattern there. There's a quick little sketch. This means the range of this function is the set of reasonable temperatures in Fahrenheit greater than -3. So our y values are reasonable temperatures greater than -3. Remember, y is range and x is domain. Okay. Now find the value of y when x equals 8. But why 8? What do you think we're using 8 for? You can plug this in, see what happens, and if you didn't come up with something, maybe this will help. Y equals 16 minus 3, which gives us 13. So assuming the temperature continues to increase at the same rate, the temperature at 2 p.m. will be 13 degrees Fahrenheit. The graph of the function of x, f of x, equals 2x minus 3 is a line. A linear function is a function whose graph is a line. Let's think about, if you're thinking about why we're using 8, if we go back, does it save it? Yes. This continues to grow for the next 6 hours at the same rate. So the reason that we're using 8 is because if it continues to grow, we're showing that at 8 hours, we are at about 13. So there's lots of reasons. You guys can just note that down. Okay, we're going to move on to, does the function realistically represent the temperature? Well, the function has a slope of 2, which represents the temperature rising each hour. However, when the sun sets, it's unlikely that the temperature is going to continue to rise. So it's really only realistic for a portion of the day, right? Because it's not gonna rise every hour for 24 hours. It rises and then it goes back down again. So we can think about what we would actually want to have for our domain. And maybe that's where that 8 comes in, right? Because for about 8 hours, maybe the temperature increases, but then it's going to start coming back down. Okay, so your turn. Sketch a graph of each function. Hopefully your graphs look a lot better than mine. And try them out and then come back when you are done. And this is now, you're on page 55 for this. All right, example 4. So here we have, we're going to be using linear functions to solve problems, real world problems. We have a chairlift. It's starting a half a mile above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? Well, we need to know what the speed is, right? So if we look over here, The chairlift travels 6 miles per hour. It takes 15 minutes to reach the top. So that gives us, I think, everything we need. It's starting here. So T is the time in minutes. The speed of the chairlift is in miles per hour, so we need to convert that to miles per minute because T is time in minutes, and we need those two unit rates to be the same. So that means that it's going 1/10 of a mile per minute. The distance traveled, so D of T, distance traveled, equals the rate of the chairlift times the time, the minutes, so 1/10 of a mile per minute, plus the distance from the base, which is like where our y-intercept is, because that's where it's already starting. It's not starting from 0, it's starting from half a mile out. Okay, so now let's compute. The distance of the chairlift from the base of the mountain at any time is represented by the linear function d of t equals 1/10 of a mile per minute plus the half a mile that it's already at. Evaluate the function. And when we solve for this for 10 minutes, we are at 1.5, and not just 1.5, but 1.5 miles from the base of the mountain, right? Because that's what it's asking us, from the base of the mountain. Okay, so writing the function, doing any conversions if you need to within the context, and then solving it for whatever it's asking in the problem. Those are our steps. In example 4, how would the function, graph, and equation change if the speed is 4 miles per hour? What is the effect on the domain? Remember, domain is x, which means in this case, it's the time in minutes. So I'll give you, take a few minutes to work that out in your book. That's still on page 55. And you can work it out. You can create a function, you can solve it or however you want, and then you can explain it. But I want you to, give reasons, give an explanation of reasons on how the function, graph, and equation change when the speed changes. What does that do? What effect does that have? And also remember to do those habits of mind at the ends of each page. Reflecting. Pause, come back when you're done. Okay, so when you turn the page, you're on page 56, you've got some do you understand questions and do you know how questions. These are just like practice, so take, I don't want to say as long as you need, but you should have plenty of time left still. It's a block day. So go through and work these out. You can go back and review examples and anything else in the video, rewind as you need to. Then I want you to, when you're done with page 56, you are going to go into Envision Online and log in. And I've assigned a 3-1 quiz and a 3-2 quiz. So I'd like you to complete both of those. Those are lesson quizzes. And this is just for you to see where you're at and for me to see where you're at with learning all of this. There's remediation work that gets assigned to you. You can watch Virtual Nerd. So any of the questions that you get wrong, go back and complete the additional activities so that you're getting the content and learning it. Because when I come back Wednesday, we are not going to be able to review these 2 lessons. Like those need to be done and we have to move on to 3-5 because we're skipping 3-3, 3-4. But so your options, if you're stuck, are to do Virtual Nerd videos. There's extra practice and examples that the computer will issue to you. So you'll complete any remediation work online and review your notes, review anything that's in your workbook, things like that, and make sure you understand it. When all of that is done and you've got a good grasp on these two lessons, then I have a Desmos lesson assigned to you in Teams. It's in the assignments, and in the directions you'll see that I only want you doing that once you're feeling good about these two. And then if you get all of that done and you still have time, I want you to, what do I want you to do? I think I'm going to have you go in and do 3, 5, nope, 3, 4, sorry, 3, 4. Go through and start previewing 3, 4 online. We'll say preview online. Okay, that should be plenty. You guys should be very busy, and I will see you Wednesday. I hope that you have had a good day with the sub and you're behaving and you've been on task. Remember, we're in the last week of the quarter, and Wednesday when I come back, we're going to discuss your tests and reflections and all of that and how that's going to work. But reflections will be counted towards your grade for this quarter. So that means they have to be done by Friday. I hope you guys had a great fall break, and I will see you soon.